Hi everyone, we're Team ARoboT and we're building autonomous pixel art builder. So our motivation is that we often see beautiful pixel art in Minecraft and we want to build it with the real robot in the real world. So here's our approach. We'll turn an image into a 6x6 pixel image and we will try to build it in the real world settings. So here's our setup. The workspace is separated into picking area and building area. The Panda arm is equipped with a D435 dash camera. So with the camera, the arm can know the pose and the color of the blocks. And every time the Panda arm will pick the correct blocks and put it onto the building area. After every build, the webcam will check current state to the plan like given by the planner. And if the current state is not as planned, the webcam will send the current state to the planner to ask it for replan according to current state. So here is our system architecture. The bidirectional arrows means it is implemented using raw service. So the flow is the main node will control the entire flow of the system. The main node will first ask the planner to give a plan according to current state to the goal state. After it gets the plan, the main node knows which block to pick up, so which color of block to pick up. So the main node will ask block to post service to transfer the block to the coordinates into a 3D coordinates. And with all the block pose and the color, the main node can ask the move it action node to pick out the block. After pick up the block, the main node can also ask move it action node to put down the block. And after every build, the main node will also send out requests to state checker to check current states. And if it's different from the plan, the state checker the main node will ask the planner to replan according to current state. So for block detection, we're using HSV color model to differentiate different colors, and we can find the bounding box and the pose of the blocks. For state checker, we first warp the image to make the state looks more clear, and then we will check if it's occupied. So 1 means there's a green block there, and 2 means there's a black block there. So if it's -1, then it is unoccupied. So for our planner, we're using symbolic planning. We have a heavily tuned heuristic value, and it boosts our performance in speed. So here's our heuristic. So HR means the pre-computed number of removal blocks in a mask, and N0 are live computed number of empty positions in a mask. So it is not admissible, but it is a fast heuristic. And when it comes to the main node, we implemented with other node communicate using raw service because we want it to be a sync process. It allows the nodes to wait for each other. So make sure every execution is done, then we move on to next step. So the moving action node is implementing RT Connect Planner. As you can see here in the office, the block to post node successfully detect the block and the color of it. Now the arm will move to the pre-grasping post that is directly above the block, and then it will move down to grab the block. So here comes our demo. So the goal state of our demo is this, and here's our forward function. As you can see, it is gradually building the block, building the art using pick and place. And here's another demo of our recovery scenario. Here you can see the blocks are not as planned. The current state should look like this, but here's the current state. We swap the blocks, and here's our robot will do the recovery. So it will first take out all the blocks below the wrong block, and then put the correct block, and then rebuild the rest of the part. And here's our recovery scenario 2. The current state should be like this, but instead we put a green block here and a black block here. So you can see the robot smartly transfer the green block to here, because that is more heuristic, and it will build the rest of the artwork. So here are some solved challenges we faced. It is that the movie planning group stops at hand link, while the gripper is actually on panda and effector frame. So we add a hard-coded offset to grabs at the correct pose. And for camera calibration, the camera mount is a little bit loosened, so we use clamp to bend it to be perpendicular, and we also screw it to security friendly. And there are side virtual walls, and we actually didn't solve this. We just have to move the blocks toward the middle of the table to avoid it colliding with the virtual walls. So yeah, that's all. Thank you for your time. We're Team ARoboT.